Okay, so in the last part, I'll show you another example application for text mining. And then we are done for this time. So let's go back to analyzing scientific documents, specifically biomedical documents. In the beginning, I told you about PubMed, this huge database of all kinds of biomedical publications. And the specific issue here that we are interested in is, again, mutations. So in this case, mutations on proteins. So there is a document with the ID 145924457, and it contains exciting statements such as the ones you can see here: glutathione S-transferase fusion proteins in Escherichia coli and putrefied BCSH agarose affinity chromatography, mutant Q15K W37R and mutant Q15R W37R showed comparable activity for NAD and NADP with an increase in activity nearly threefold over that of the wild type. So again, because of COVID, some of these terms are actually more familiar to you now probably than they were a year ago. The wild type is the original version of the protein, and the mutant has some changes. And because of the changes, some properties change. In this case, the activity changes, and it changes by increasing threefold compared to the wild type, the original version. And the mutations show you which part of the genome were changed from what kind of amino acid to what other kind of amino acid at a certain position in the DNA. So here you can see the different entities that are relevant. You can see the red entities. These are enzymes. The ones in orange are mutations. The ones in blue are organisms, and so on. So what is interesting to extract for automated processing of all of these documents is you want to find out the basic entities, organisms, mutations, enzymes, properties, physical quantity, the impact expression, and what the impact was actually doing. So before, you've seen how to extract entities. Now you can implement this just like before, except it's different kind of entities. It's not about persons and organizations and universities. It's about proteins, mutations, enzymes, and so on. So this is again interesting because these information are something that you need for various research purposes. And this is something that people used to extract by hand manually. Now you can see people going just manually reading these publications to stay up to date with research, and then they would put it manually into a database. One example is Brenda, the Braunschweig enzyme database. And then in there, you see references to the publication, and again, the details on what was described in the publication, like here a 100-fold increased activity. But because this was done manually, the actual entries in the database are years behind the current research. Now, by the time somebody has time to read through it and enter it in this database, already hundreds and hundreds of new publications have been published. So for this reason, it's important to have these automated machine reading approaches, even as a first step that are later then checked for accuracy, basically. And you can see in the database which ones are created manually and which ones are just created automatically. So as just one example, how do you find an organism expression? So again, these can come in different forms. The typical pattern for an organism is a genus, followed by a species, optionally followed by a strain, like here, Escherichia coli of strain XL1 blue. Sometimes you see an old species, an old genus name like Aspergillus added in brackets here. So this is pretty much standardized, how you describe an organism in a text. And when we did this, we just looked at the different rules and expressed these in, again, in patterns that are fed into a transducer. So there can be a genus, a species, a subspecies, and optionally a strain, and some variations on it. And with this, you can find, with a very high accuracy, all the organism mentions in a document. For the other entities, it's a bit more complicated, so I'm not going into it here, but we implemented all of this and then ran it on a subset of PubMed. At that time, it was 500,000 documents you could download, the so-called open access corpus. And once you have all of these semantic annotations, instead of manually going through all of these documents, you can now run a query against it using a document query language. For example, if now a scientist has a question like, I want to know all the protein mutations that affected the property of the protein, which is the affinity, you can write this in form of a query. What is the impact over the affinity annotation? And then it will pull out over 500,000 documents exactly these 6,999 mentions. And this is not the full document. It's the precise location in a document where this is being mentioned. So this is a lot more precise and a lot more targeted. And you can write lots of different questions in form of queries. So this is actually quite old work that I did with master students more than 10 years ago. If you're interested, you can have a look at how a text mining system as a master's thesis project looks like in the Spectrum library here. So what have we done today? I told you about text mining as an application of natural language processing, and we also looked at the individual steps that you do as part of such a system, and you can reuse these steps for other applications like building chatbots, for example. So this is quite nice because this is a domain where we now have very mature libraries, tools, resources that you can use directly to build robust, scalable systems. If you just want to make a basic system demo, let's say a company has a problem, they want to find certain information in their document, often you can use some quick rules to have a demo for the system. Now, if you know what you're doing, you know Spacey, you know all the other tools, you can get something together in a couple of hours. Of course, if you want to do it for real, if you want to look at complex, sophisticated entities like in the biomedical analysis, some of those are still open research problems. It can range from very easy to something that takes you a year of work. What I haven't really covered here is instead of using libraries and tools locally, there are now also quite a few online cloud APIs that you can use. So again, this is convenient, but you are tying your implementation to a specific cloud API. You cannot just switch from one provider to another. And often for companies, confidentiality is another issue because you are sending your possibly secret company documents to a cloud API. They will tell you that they are all private and confidential, but do you really trust them? Well, for this reason, very often companies decide to have the pipelines in-house. What's interesting is, even though this is a relatively mature AI technology, many businesses don't know about the potential of extracting knowledge from their documents. Every company has tons and tons of documents that they produce, that they use, but not all of them use AI for even basic entity extraction. So there's quite a bit of consulting potential here. So what should you read? There is a nice chapter on information extraction in this book that you can get online, the Natural Language Processing in Action book. And additionally, for machine learning annotation, the book that I think I mentioned earlier here, Natural Language Annotation of Machine Learning, is really good. And finally, if you want to know a bit more about dependency parsing, you can have a look at the book here, Speech and Language Processing. For the 3rd edition, which isn't out yet, you can get a draft online that you can download, which is quite nice. And in chapter 14, you can read a bit more about dependency parsing. So have fun with that, and I'll see you again in the next lecture.